You know that feeling, right, when you're in a car and someone just slams on the gas? That lurch? Or have you ever stopped to look at the perfect, graceful curve of a hanging chain? Well, it turns out those two things are connected by a secret mathematical language. And today, we're going to decode that language. We're going to uncover this incredible link between the physics of how things move and the basic shapes we see in nature. So let's dive in.
Okay, so we all get speed, right? Velocity. And we get acceleration. You push the pedal, the car accelerates. You hit the brakes, it decelerates. Pretty simple. But what do you call that feeling when the acceleration itself suddenly changes? You know, when you go from just cruising along to suddenly flooring it? You call it a jerk. And no, that's not just some slang term. That is the actual scientific name for it. It's that jarring feeling, the one that tells you the forces on your body are changing, and fast. You can always tell an experienced driver because they're smooth. They minimize the jerk. A new driver? Yeah, their ride is full of it.
But jerk is really just the beginning. It's like learning the letter C in a whole new alphabet that describes the subtleties of motion. So let's build out this vocabulary, one step at a time.
Think of it like a ladder. At the bottom, you have your position. The rate of change of your position, how fast your location is changing, is velocity. The rate of change of that is acceleration. Now, we just take one more step up. The rate of change of acceleration is what we call jerk. So in math speak, it's the third derivative, and it's basically our tool for measuring the smoothness of any movement.
So what happens if we climb another rung on that ladder? What's the rate of change of jerk? Well, that's called snap. It's the fourth derivative. If jerk is about how suddenly your acceleration changes, snap tells you how suddenly that jerk changes. We're really starting to get into the super fine details of movement now.
And believe it or not, it keeps going. The next two steps up, the fifth and sixth derivatives, are actually called crackle and pop. And the best part? Physicists literally named them after the Rice Krispies cereal characters. It's a pretty fun way to remember these higher-level ideas, right? Snap, crackle, and pop.
So here it is, our whole alphabet of motion all laid out. We start with position, and then each step down is the rate of change of the one before it. Velocity, acceleration, jerk, snap, crackle, and pop. It's an amazingly precise way to describe how things move. Now hang on to this idea because we're about to connect it to something that seems totally unrelated.
All right, let's totally switch gears. I want you to forget about jerky cars for a second and just look at the world around you. Think about power lines hanging between two poles, or a necklace resting on your neck, or even a spider's web. They all make the exact same beautiful natural curve.
That curve actually has a name. It's called a catenary, which comes from the Latin word for chain. It's the shape any flexible chain or rope naturally forms under its own weight when you hang it from 2 points. It looks a little like a parabola, but it's not. It's its own unique, fundamental shape, and it's everywhere in nature and engineering.
So, how does math describe these shapes? Well, look on the left. We've got the circle, defined by our old friends sine and cosine. And they're linked by that famous rule, cosine squared plus sine squared equals 1. Now look at the right. The catenary curve is described by a different family of functions, hyperbolic sine and cosine. And look at their rule. It's almost identical. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. That tiny little switch from a plus to a minus is the only thing separating a perfect circle from this fundamental hanging curve. It's a huge clue that these ideas are deeply connected.
So we have this alphabet of motion: jerk, snap, crackle, pop. And then we have this essential shape of nature, the catenary. What on earth is the bridge between them? Well, the answer is one of the most powerful and important numbers in all of mathematics.
This is it, the big question. How can the math that describes a lurching, jarring car ride also describe the elegant, graceful curve of a hanging chain? I mean, it seems like they come from two different universes, but the connection is absolutely beautiful.
The secret ingredient is the number E, Euler's number. It's the mathematical constant that underpins all continuous growth and change. So how does it connect everything? Well, remember those hyperbolic functions that define the catenary curve? Just look at the formulas. They are built directly out of E. They're just simple combinations of e to the power of x. And that is the mind-blowing link. The mathematics of change, jerk, snap, pop, and the mathematics of form, the catenary, are both built from the exact same ingredient, the number E.
Okay, so this is way more than just a neat math trick. Understanding this deep connection between the alphabet of motion and the shapes of nature has some absolutely incredible real-world applications. Let's take a look at how this hidden language is actually being used to build our future. First, let's go to space.
When a satellite needs to change its orbit, any sudden jerky movement is a disaster. It wastes precious fuel and it puts a ton of stress on its delicate instruments. So engineers plan trajectories that minimize jerk and snap, creating these incredibly smooth, ballet-like maneuvers that are way more efficient.
Now check out this robotic arm. It doesn't matter if it's assembling a microchip or performing surgery, its movements have to be perfect. By controlling these higher derivatives, engineers can eliminate tiny, damaging vibrations. This means the robot lasts longer, and more importantly, it can perform tasks with a level of precision that is literally superhuman.
And this brings us right back to where we started, the car ride. Automotive engineers are obsessed with analyzing vibrations. They study jerk, snap, and even crackle in a car's suspension when it hits a bump. All that math helps them design cars that give us a smoother, more comfortable, and much safer ride. It's all about controlling those rapid changes.
And maybe the most important application of all is that this math saves lives. During an earthquake, the ground doesn't just shake, it jerks. A high jerk value means the shaking is violent and unpredictable. By understanding these forces, engineers can design buildings and bridges that can absorb that energy and withstand those shocks, making them far more resilient.
So we've really come full circle, haven't we? We started with a simple feeling in a car and ended up with the equations that describe the shapes of our universe. We've just had a peek into a hidden, unifying language all around us.
So what's the big picture here? Well, we learned that everyday feeling of a jerk is actually part of a whole mathematical alphabet for motion. Then we found out that this alphabet is secretly connected to the natural shapes we see everywhere, like the Catenary curve. And the bridge, the secret ingredient that links them all, is the number E, the constant of continuous change. And finally, we saw that understanding this language isn't just for fun, it's absolutely vital for building the modern world.
This whole journey, from a simple lurch to a hanging chain, it just goes to show you there's this deep, beautiful order hidden just beneath the surface of things. It really makes you wonder, doesn't it? What other parts of our world are governed by a mathematical language that we're only just beginning to understand?